In this lecture, we want to look at binary heaps and then finish with a look at using binary heaps to sort an array. A binary heap is a logical abstraction. That is, the underlying data structure is an array. However, the abstraction is a binary tree. So we have a binary tree that's actually stored in an array. Heaps can be max heaps or min heaps. They're designed really to provide efficient insertion and removal operations on an array. Normally when you have an ordered structure such as these are, you have a very slow insertion or deletion operation with an array. That is, if we're going to insert an element into an ordered array, we can find the insertion point fairly quickly by using binary search. However, we must shift array elements down out of the way to make room for the new element to be inserted. And this shifting operation is big O of n. Big O of n is really too slow for very large structures. Therefore, binary heaps provide a more efficient mechanism for doing this. So we have efficient insertion and removal. And it turns out that the removal and insertion is in big O of log n time. The removal operation always returns either the maximum or the minimum element in the heap. Removal of a specific element from the heap is not usually supported. The primary use of binary heaps is for priority queues and also for sorting. So there are two properties we want to look at, structural and ordering. With the structural properties, each node has 0, 1, or 2 children. This is the same as a binary search tree structural property. The tree is complete. All levels are full except for the bottom level, which need not be full. And if that bottom level is not full, then all nodes are left justified. Then we have the order properties. Every child is smaller than its parent for max heap, and every child is greater than its parent for min heaps. So here we have an example of a min heap and a max heap. In the case of the max heap, we see that the 50 here is actually the largest element in the structure, and it is at the root. The requirement then is that each child be smaller than its parent, but there's no other ordering specified. With a binary search tree, everything to the left must be smaller and everything to the right larger. However, this is not a binary search tree, it's a binary heap. And therefore this would not satisfy the binary search tree properties at all, but it does satisfy heap properties. The only requirement then is that the children are smaller than the parent. Thus we have 42 and 13 smaller than the 50, 33 and 7 smaller than the 42. For the min heap, it's the reverse. The smallest element at the root is the smallest element in the structure, and the children of every node must be larger. Thus with the 6 we have the larger children, 17 and 27. With the 17 we have the 22 and 19. Again, there's no specification as to which side a larger or smaller element must go. Thus the smaller element, this 19, is on the right, and the larger element, the 22, is on the left in this particular case. But that's unimportant. The only requirement is that these nodes actually be larger than the parent node, which is the 17. Notice too that the bottom level is not completely full, but the nodes are left justified. Thus, to have these two nodes off the 27 would be an error, because you can't have the spaces here. The nodes must be left justified. So here is a min heap and the array that's used to store it. The heap here is actually an abstraction, and the array where it's actually stored is down here. By abstraction, I mean this is an ordered structure. The smallest element is at the very top of the structure, And if we remove from this heap, we will always get the smallest element that remains in the heap. Therefore, it is in order. But if we look at the array, it doesn't seem to be in order at all. We have 6, 17, 27. So far, so good. But then we have 22 and 19. So the array is not ordered at all, but it is in fact, heap order. The way this works is, starting with the root at index 0, the array goes in level order. That is 0, then 1, 2, then 3, 4, 5, 6, 7. So this is the way then that binary heaps are represented in the array. So to manipulate these elements in an array while keeping the heap properties in mind, we need to be able to identify the parent and child indices of the elements. So here are the formulas for doing that. The parent index is current size minus 1, and right shifted 1, which is division by 2. This is just a bit shift. It's actually division by 2. The left child is 2 times the index plus 1. The right child is 2 times the index plus 2, or the left child plus 1, of course. Thus, if we look at the heap here, the indices where these go is 0, 1, 2, 3, and 4. So our formula is for the parent is index minus 1 over 2, or right shift. So the parent here, 2 minus 1 is 1. 1 over 2 is 0. 1 minus 1 over 2 is also 0. And here with the 4, 4 minus 1 is 3. 3 over 2 is 1. This is integer division. 3 minus 1 is 2. 2 over 2 is 1. So this gives us the parent index. Then, to get the left child, we're using the formula 2 times index plus 1. So here, with the 0, 2 times 0 plus 1 is 1. Here, 2 times 1 is 2, plus 1 is 3. Thus that will give us the left, and then the right child is just the left plus 1. This makes it easy to get to the left and right children, and also the parent, which allows us to manipulate our heap. So, to insert into the heap, we insert a new element at the end of the array. This corresponds to the next available slot in the bottom level of the tree. Or if a new level is started, then it's the leftmost one. So the element is inserted at the very end, but that doesn't mean it's in the right place. It may be in the wrong place. If this is the case, then you must restructure the heap in order to get the element into correct location. So the operation required to move this newly inserted element into the correct location is called trickle up. So we compare this element with its parent, and if it's out of place, that is, it doesn't satisfy the heap ordering property, then we swap it. This process continues up the tree until the heap ordering property is in fact satisfied. Because the number of levels in a full tree is exactly log n, this means that the maximum number of steps required to get the tree back in a valid heap state is big O of log n. So let's take a look at the insertion here. I'm going to go ahead and set a list of random elements, 14, 2, 18, 6, 7, 3, 19. So we're going to insert these in the heap and see how it is built. First we insert the 14. And then our array over here. We have 14. So this one is inserted. Now we insert a 2. The 2 has to go in the next slot, which is right here. Recall that the heap must have the bottom level left justified. You could not possibly put the element here. It can only go here. So this is array index 0. This is array index 1. So we have inserted our 2. And then we need to make a min heap. So we'll consider that this is a min heap. And we look at this and we say, is this ordering property satisfied? That is, with a min heap, children must be larger than their parents. This is not the case. Therefore, we swap the 2 and the 14 to restore this to the heap state, to a valid heap state. So we swap the 2 and the 14. Here we have the 2, then the 14, and similarly our array here. So these two elements then are switched, and we have the 2 at index 0 and the 14 at index 1. So now we have the 2 in place. We insert next the 18, and this is at index 2. We insert the 18. We now see if we have satisfied the heap properties. The 18 is in fact larger than the 2, so we're all right. We don't have to do any shifting. We have that one inserted. The next one here is the 6. So it goes in last position. We have to start a new level, and it goes in the leftmost slot. So this corresponds to index 3. So now we go here and put our 6 in the array at index 3. Now we must examine to see if heap order is satisfied. And heap order requires that children are larger than their parents. So we look at the 6 and 14 and see that this is a violation. So we must swap the 6 and the 14. So we're swapping then the 6 and the 14 so that we restore this to heap order. Six and 14. Okay, so the 6 now is in the proper order. It is not smaller than the 2, so there's no need to swap that. Next we insert the 7, and it must go in the next available slot at index 4. So here we have the 7. Now we examine this and we see that it is in fact larger than its parent, the 6. So this is okay. The 7 is inserted and we're good to go. Now we insert a 3. And this is at index 5. And so we examine the parent and we see that the parent is larger, but the requirement is that children must be larger than their parent. Therefore, we must swap the 3 and the 18 in order to satisfy the heap property. So we swap the 18 and the 3. And then, of course, these are swapped in the array. And then we have the 3 inserted, and we're in good order. Finally, we insert the 19, and it must go here. And this is at index 6. And we look and we see that this is in the proper heap order, so we're good to go. So we have now built our heap and our array in big O of n log n time to do insertions, to do the in insertions where each element costs log n time. Removal. So the removal is designed to return either the larger or the smallest element in the array. So the element at the root of the tree is removed. This is the element at index 0 in the array. This does leave a hole where the element had been. So in order to deal with this situation, the element in last position in the array, that is the rightmost element on the bottom, is moved and placed into the root of the tree. Once this is done, it's entirely possible and perhaps probable that this element will be out of order. So then we must perform what is called trickle down. That is, we check the two children of this node, and if either of the children is smaller, we swap with the smallest child. So the swapping continues until the heap order property is valid. So let's look at the just created heap and look at the removal operation. Okay, so in order to remove, first we will remove, these have all been inserted, we will remove the 2. So we do that, the 2 is gone, and we have a hole that must be filled in. So we take the last element in the heap, which is the 19, and put it in the root position. We fill in the hole. So this has now been removed, and this ceases to exist. So it's important that you decrement current size and do not look at this element again. It's not necessary to set this location to null. So you in fact will still have a 19 here in this array, but it is no longer logically part of the heap. It's garbage. So we go to our 19, and it's not in proper position because it must be smaller than its children. So we have a 6, we have a 3. We must swap with the smallest child. So we swap the 19 and the 3. We swap the 19 and the 3. So this puts the 3 at a root, the 19 here. We swap the 3 and the 19. Now we keep going and we examine the children of the 19. The 19 has only one child, which is the 18. The 18 is smaller, therefore it must be swapped. So we swap the 19 and the 18. We swap the 19 and the 18. And again, heap order is restored. Now we remove the 3. So we take the 3 out. And again, to fill in the hole, we must go to the last element in the array here, the 19. So we're going to take the 19 and remove it from the heap and place it in root position. So we put the 19 in root position and remove it from the heap. So again, we must look at the two children, and if the children are smaller, we have to swap with the smallest child. The 6 is smaller, so we must swap the 6 and the 19. We swap the 6 and the 19. So then we swap the 6 and the 19. Now we examine this and see if we need to swap again. So we see that the children are smaller, but they can't be. They must be larger. So we swap with the smallest child. Candidates are the 14 and the 7. The 7 is the smallest child, so we swap the 19 and the 7. We swap the 7 and the 19. And now the heap condition is again satisfied. So then we remove the 6. So we remove the 6 here, and we must fill in the hole. So we take the 19 from here and put it here. So the 19 goes in the root position to fill in the hole, and this is removed from the array. We have a 19 now at index 0, and the 19 here is removed from the array. Now we check to make sure that we have the proper ordering. We do not. The 7 is smaller than the 19, as is the 18. So our two candidate children are 7 and 18. We swap with the smallest child. We swap the 7 and the 19. So we have swapped the 7 and 19. We swap these here as well in the array. 7 and 19. Now we examine to see if we must keep going. Well, it turns out that the 14 is smaller than the 19, so we must swap them. So we swap the 14 and the 19. And in our array, we will swap this representation as well. 14 and 19. And the heap condition is again restored. We now remove the 7. So we remove this 7, and in its place we put the 19, which is at the end. This is then removed. So we now have the 19 at index 0. So we must check to see whether or not the heap condition is satisfied, and it is not, because both children are smaller than the parent, but they must be larger. Therefore, we have two candidates for a swap, the 14 and the 18. We swap with the smallest child. So now we have 14 and 19. We have swapped them. And here we have 14 and 19. And we check to make sure that heap order is satisfied. In this case it is. The children are larger, so no swaps are required. And we're good. So next we remove the 14. When we remove the 14, we take the last element and put it in its place, which is the 18. So we now have 18 here, and this is removed. The 14 is removed from the heap. The 18 placed at index 0. This is gone. Now we check to see if we need to swap, and we do not, because the child here, the 19, is larger than its parent, so it's fine. Then finally we remove the 18. The 19 goes in its place. And the element at index 1 is removed from the heap. Now we're left with a single element in the array, which is our last removal, and we have now emptied the heap, and you will notice that these have come out in sorted order. We have always removed the smallest element from the heap in turn each time we have removed the smallest element. So this code can be just a little bit tricky to write, and some things that you need to watch out for when you're writing the trickle up and trickle down methods. First, you have to make sure that you don't run off of either end. When you're trickling up, you want to make sure that you do not run off the top of the tree. When trickling down, remember that you may have 0, 1, or 2 children. Also, you should never test an array element to see if it's null. Rather, you should use the current size variable to keep track of the end of the heap. When you're removing things, you will have garbage left over in the array. And if you run past current size, you can pull elements up into the heap that may have been already removed or duplicated. So you must make sure that you don't run past the end of the heap. Also remember that not all trickle up or down operations will go all the way to the top or all the way to the bottom. You may need to stop somewhere in the middle, so watch out for your stopping condition. Finally, there is a more efficient way of handling these swaps. Rather than swapping elements, what you can do is shift until you find the place where it goes and then drop it in. And that's somewhat more efficient. Heaps are not stable. This is not a concept you may have discussed so far in the course. Stable has to do with how duplicate elements are handled in an array, or in this case, in a heap. So I'm going to switch over to the sketch pad a moment here so we can look at this. Imagine that we have this scenario with the min heap. We have 2 and then we have 3 3s. Alright, when we remove these elements, obviously the 2 is going to come first, but now which 3 goes next? Which 3 is the next one out of this heap? Stability says the first 3 that was inserted into this heap must be the first 3 that was removed. We cannot, based on the position of these 3s, we cannot determine which one has been in the heap the longest. Which one is the 3 that came into the heap first? It's not possible to know. It could in fact be any of them. Therefore, this is a problem of stability. For some problems it does matter. Therefore, if it's important that the first 3 in the heap is removed first, then you must have some other mechanism for determining which one came in first. And so the way you have to do this is with a wrapper class. This is the start of the binary heap that uses a wrapper class. This wrapper has 2 elements in it, an entry number, which is a long integer, and then the element E. So when you make this wrapper, it holds 2 things. It holds the data, and it also holds a sequence number. So what this concept does, what this adds essentially, is that instead of the single element E here, which are the 3s, we add a secondary field, which is the insertion order, such that here we have, for instance, we might have something that looks like this. I'm going to add the number to the 2 as well. 2, and then 12. 3, 7, 3, 19, 3, 27. So the bottom numbers are sequence numbers. That is, the 7 was inserted first, then the 19, then the 27. In this way, we can keep track of which elements that are normally duplicates were inserted first. So then when we remove, we'll remove the 2 with the sequence number of 12. Then we remove the 3 with the sequence number of 7. Then we remove the 3 with the sequence number of 19. Then remove the 3 with the sequence number of 27. This allows us to keep track of which 3 was inserted first, and this gives us stability. So here's our wrapper class. We have an eData along sequence number. Then in the constructor, we increment our entry number, which was the class level variable used here, entry number set to 0 to start with initially. And then every time there's a new insertion, this is incremented. And so we have here the sequence number, the number or the order in which each element is inserted. Thus, the sooner an element is inserted, the lower its sequence number will be. I also want to call your attention to the compare to method. We normally would not put a compare to method in a data structure. That is, we would not put a compare to method in a binary heap. If we did that, what we would be saying is we want to write code to compare two binary heaps. But a compare to method inside a binary heap would not compare the elements, it would compare the heaps. But we need a compare to in class wrapper here so that we can arbitrate between elements that are the same. So our first comparison here is to see how the two objects compare. This is based on the compare to method inside the objects, the E that's inserted in the heap. So we compare these, and if they're equal, you have 2 3s for instance, then we use the sequence number to break the tie between them. And if they're not equal, then we just use the comparison between the two data elements. So for instance, if we have a 1 and a 2, then the 1 is less than the 2. If we have a 3 and a 3, then the sequence number of 1 is less than the sequence number of the other, and that's what's used here. In the case where they're equal, then the sequence number is used. Otherwise, the data elements themselves are just used. The heap structure can also be used to sort an array. Insertion of one element into the heap is log n. That is because the height of this heap is in log n. Therefore, you can do no more than log n operations to restore this heap to a valid condition once you do an insertion. So if one insertion is log n, then n insertions is n times log n, which is n log n. Removal, similarly, removal is log n. So if you're removing n things, you have n times log n is n log n. So the process then for using a heap to accomplish a sort is you insert each array element into the heap and then you remove them all, and they will come out in sorted order. So the steps required then, first the insertion, n times log n, plus the removal, n times log n, is equal to big O of n log n. You always want to use a max heap for sorting. So let's look for a moment at this process and see how it works. So I'm going to draw a max heap here, which means the largest element is at the root of this tree. So I'm going to put a 50, and then the children must be smaller. 32, 27, 16, and 8. This is enough elements to demonstrate, and let me write our array down here. So we have 5 elements. And we can go ahead and wipe out this piece. All right, so we have 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Filling our array, we have 50, 32, 27, 16, and 8. So the way heap sort works then is we remove the maximum element from the array. The root element, which is the 50. This is now removed. And recall that we will fill the hole with the guy at the end, which is the 8. So the 8 goes here, and it is now removed. So now the heap is one smaller. The heap is one smaller. The 8 is here. Our heap has 4 elements. Therefore, this part of the array is the heap, but index 4 is not there anymore. So we drop in the 50. Now we have to do the trickle down. That is, we have to make sure that the largest element is at the top of the heap, so we swap with the largest child. We have the 8, the 32, so we must swap with the largest child. We're going to swap with the 32. So we swap the 8 and 32 here. Again, we look at our structure and we see that it's not in order yet. We have 8 and 16. These must be swapped, so we swap the 8 and 16. We swap the 8 and 16. And the heap condition is now restored. Now we remove the 32. So we remove the 32 here. "32" has been removed, and in its place goes the 8. In its place goes the 8. The 8 is removed from the bottom position and placed at index 0. The 8 no longer is here. This is one smaller. The heap now has 3 elements. The array has 2 elements. We drop in the 32. Now we must examine this to see if we need to do any swaps to restore this to proper heap condition for a max heap. So we look at the 2 children, and we see that the 27 is the largest child, so we must swap the 8 and the 27. We do so. We have 27 and 8. We swap the 8 and the 27 here as well. This is the actual data structure. 27 and the 8. We have now restored the max heap condition, so now we remove the 27. We remove the 27, and we place the element in last position here, which is the 8. The 8 is now removed and placed at index 0. The heap is now size 2. The array is size 3. So we can drop the 27 in right here, and then we need to examine our heap, and we see that it's not in order, so we must swap the 8 and 16. We do this. We swap the 8 and the 16. We swap the 8 and the 16. Now we remove the 16. So we remove the 16, and this makes the heap one smaller. It now has 1 element. The 16 is out of there. And we fill the hole with the element at the end, which is the 8. It is now out of the heap. The heap is size 1. The 8 is here. We drop in the 16. Now, as you can see, we've only got one element left, so we can pull that out of the heap, and we're done. We have now sorted the array, and so by using a max heap, with each operation, the heap becomes one smaller and we drop in that largest element. The heap becomes one smaller, we drop in the largest remaining element, and so on until the array is sorted. This wouldn't work with the min heap because you would have to shift. If you dropped into index 0, then you would have this part be the array and this section be the heap, which would not work. So you want to use a max heap for heap sort.